So once again, welcome everyone to this lecture, which will be about aggregation, which is an offline methodology for approximating dynamic programming problems. And on a high level, you can understand this methodology as a form of problem simplification, where you start out with some original problem, which typically will have a very large state space. And then you simplify the problem by grouping together states into a smaller set of aggregate states. And those aggregate states then form a new dynamic programming problem, which can be efficiently solved. And then using the solution to that problem, you can then formulate a cost function approximation for your original problem using a form of interpolation. And the goal of this lecture will be to understand how we can take this basic principle of problem simplification and turn it into a general methodology for approximate dynamic programming. And we also want to understand a little bit what we can expect from this kind of approximation in terms of theoretical performance and also in terms of computational expenditure. So this is the outline. I will start by covering the simplest form of aggregation, which we call aggregation with representative states. Then I will show you an example of such aggregation for approximating a quite complicated POMDP problem. And then we will have a break. And then after the break, I will cover the more general aggregation methodology. And then I will show you how we can apply this more general methodology to a quite detailed case study in the context of cybersecurity. And this is the ongoing research that Yushao mentioned. So let me just start by briefly reviewing the notation that I will use so that we're all on the same page. I will denote the state space by capital X, enumerated from 1 to n, and the elements in general will be denoted by I and j. The control space is denoted by capital U, and the available controls at a given state is denoted by U of I. And the stage cost is denoted by G, cost to go by capital J, discount factor by alpha. And we will consider stochastic systems that are defined in terms of transition probabilities. So in the previous lecture, I believe you saw stochastic systems defined in terms of the system equation instead, with a random disturbance W. So these two formulations are equivalent, but it just turns out that in expressing the aggregation framework, it's a little bit more convenient to work with transition probabilities directly. So that is what I'm going to use. And I believe that you are quite familiar with this notation, but if there's something that's not clear, just stop me at any time. So when we are aggregating a state space into a smaller set of aggregate states, it's not necessarily going to be the case that the aggregate state belongs to the original space. But in the special case, when that holds, we will refer to them as being representative. So when you're doing aggregation with representative states, you are simply selecting a subset of your original state space to be representative. And to differentiate them from the original states, I will denote them with X and Y in general, instead of I and J. And you have a very intuitive example here in the figure where the original state space is a very dense grid. And then to select the representative states, we can simply form a coarser grid on top of that dense grid. And once we have selected the representative states, that is the first step of the aggregation methodology. The next step is then to relate these representative states to the original states. And we do that by introducing so-called aggregation probabilities. So for each original state, we define a probability distribution denoted by phi that tells us the probability of transitioning from an original state to each of the different aggregate states or representative states. And intuitively, this distribution expresses a form of similarity between different states. And we will see a bunch of examples later on in how you can define this. But in general, it is problem specific in how you define those probabilities. But for example, in the grid here, you could imagine defining it based on the Euclidean distance, for example. And these aggregation probabilities, you can think about them as defining the aggregate dynamics. So now in our system, we have two types of transitions. We can transition between original states using the original dynamics of the problem, and that is indicated by the green arrows here. And we can also transition from a non-representative state to a representative state using the aggregation probabilities. And that is indicated by the blue arrows. So effectively, we have now a dynamical system with the following transition diagram. So we can start out in some representative state X, and then we can select some control, which will incur a cost, and transition us across to a new state J. And from that state, we can then transition back to the representative state using the aggregation probability. So this means that now we have a system where we can transition from a representative state to another representative state in a controlled manner. So it's a controlled dynamical system. And this, you can now see it quite clearly, will allow us to formulate an aggregate dynamic programming problem with a much smaller state space, only focusing on the representative states. So we obtain this dimensionality reduction that we want. And before I formulate this aggregate problem in detail, let me just pause here if there's any question about this slide so far. Because if you understand this slide, this is kind of the core of the aggregation methodology. Yeah, so right now we are focusing on a particular case of aggregation called aggregation with representative states. And that's the main differentiation from the general methodology is that in this case, we assume that the aggregate state is going to be a member of the original state space. So the set of representative states, which I denote with calligraphic A, that is going to be a subset of the original state space. But later on, we'll see a more general formulation where this is not necessarily going to be the case. Yeah. Yeah, that's a very good question. So mostly in this lecture, when we present the theory, we will assume a discrete state space, but actually the whole framework generalizes the continuous spaces as well. And when we go through our experimental results, we will actually use a continuous space. So the original state space can be continuous, but then when you select the representative states should ideally be finite. Yeah.
So whenever you are transitioning from one state to another and defining it using any control, you can always represent that transition for the representative states as well by looking at the aggregation probabilities. Is there a way to map the representative states back to the original fine-grid states to figure out at least maybe what the control is taken, or if any transition in the representative states can easily correspond to the actual ground-truth states?
Yeah, so actually now when we have representative states, the transition from a representative back to the state space is kind of trivial because it's just the identity transition, since the representative state here is actually a member of the original state space. But later on, we will see that then when this is not the case, then we will need a special kind of disaggregation probability to also transition from representative to aggregate. But right now, it's just basically equality. So X equals to Y, and that's how we go back, yeah.
Just a suggestion, when you're talking about some part in the slides, could you please use the mouse?
The mouse, yeah. Good point. So any other question about this? Okay, so for the aggregate dynamic programming problem, we're then going to define the state space as being the set of representative states. The control space is going to be the same as in the original problem. And the probabilities and the costs of the transitions can be calculated using the following formulas, which basically you multiply with the aggregation probabilities. Now, from a computational point of view, there is a slight potential problem with these formulas. And is there anyone that can tell me what could be a problem computationally? So the problem is that the state space, we're working with quite large scale problems here, and we're trying to have an approximation methodology that can scale to very large state spaces. And here we have a sum over the entire state space. And that, if you're working with a state space of, say, 10 to the power of 100, that will simply not be computationally feasible. But in practice, it turns out that very often the practically relevant dynamic programming problems will be sparse in the sense that from a given state X, there's only a small subset that you can reach with a non-zero probability in one step. And therefore, quite often we can reduce this sum from 1 to n to a much, much smaller number. And that makes these calculations efficient. So once you have obtained these transition probabilities and the costs, you can then solve the aggregate problem using dynamic programming. And even in the case when you could not obtain the transition probabilities and you only have a simulator, you can also solve it using reinforcement learning or other simulation-based methodologies. So that's also an option. But in any case, since this is a dynamic programming problem, when you solve it, you will obtain a cost function, right? And we're going to denote that cost function with R star. So this is the optimal cost function in the aggregate problem. And it's important here to note that this cost function is different from the optimal cost in the original problem, namely J star. And they are different in two ways. First of all, they will generally have different costs at the representative states. And this is because the original problem and the aggregate problem have slightly different dynamics in how you transition between states. And another fundamental difference is that the original cost function, J star, is going to be defined for the entire state space. But the aggregate cost function is only defined for the representative states. So this means that if we want to approximate J star, we will need to do some kind of interpolation in order to determine what is the cost going to be for a state that is not representative, J. And we can interpolate that from the values of the representative states or the cost of the representative states. And we do that interpolation by utilizing the aggregation probabilities that we just defined. So more specifically, we can define an approximate cost function J tilde for the original problem using this interpolation formula here, where we simply weigh the aggregate cost by the aggregate probabilities. Yes, please.
You said representative states are part of the original. Okay, so current X dash and X double dash should fall on the graph.
Sorry, I didn't get the question.
You said representative states are part of the original grid.
Yeah.
So current representative for those selected should fall on the cost function graph. Why is it?
No, okay, so on the x-axis you have states. So this is actually part of your state space, this point. It's just that they have different cost values. That's why they are. So y-axis you have cost. That's why they are not. And they have different costs. That's why they are going to be, in general, different cost values in the curves here. Does that answer your question?
No, my question is why the cost function?
Okay.
It's a part of you.
Yeah, okay. So they're mainly, so they are going to be different because the dynamics of the two problems are slightly different. So if you look at this figure here, then basically in the original problem, when you take the control, you're going to stay at that state. But in the aggregate problem, you're then going to move again to some representative states. And that changes the dynamics of the whole problem. So in general, that's going to lead to different costs. So it's not this, the aggregate problem is not the same as the original problem. There is a difference there, even though they share a lot of similarities in that they have the same control space and so forth. But the dynamics are slightly different. So that's why in general, the cost to go from a representative state in the aggregate problem will in general be different from the cost to go from the same state in the original problem. Okay, so this is the interpolation formula. And that's how we obtain our cost function approximation. And once we have the cost function approximation, we can then combine that with, for example, online play and many other online methodologies that you have discussed in the course to derive policies. For example, a one-step look-ahead policy, but there are many other options here as well. And this is then how we approximate the original problem using the solution to the aggregate problem. So now we have a cost function j tilde and a policy, both of which can be applied directly to the original problem based on the aggregate solution. But one fundamental question remains, and that is, how good is this approximation? So in other words, how close is our approximation j tilde going to be to the optimal cost function j star? And that will be the topic of the next couple of slides. Now, this difference between j tilde and j star is going to depend on the aggregation probabilities. So for the purpose of our analysis, we will focus on a special case which we call hard aggregation, where the aggregation probabilities are going to be 0 for all representative states except one. So in other words, for each original state, that's basically going to aggregate or be associated with a unique representative state. So basically a hard aggregation means that probability of going to one representative state will be 1 and 0 for all the others. And this now means that we can partition the original state space by grouping together states that aggregate to the same representative state X. And we're going to call that group or that set of states the footprint set of X, and going to denote it in general with S of X. So all of these footprint sets are going to be disjoint, and their union is going to cover the entire state space. And if you now look at this definition of the aggregation probability here in hard aggregation, and then you plug that into our interpolation formula, then it becomes quite clear that for all of the states that are in the same footprint set, they're going to have exactly the same approximate cost in j tilde. So in other words, j tilde is going to be piecewise constant, as shown in this figure here. And this gives us quite a lot of intuition about the question that we're interested in, namely, what is the difference between j star and j tilde? And now, if you look at this figure, you can see that the difference is mainly determined by how much j star varies within these footprint sets. If j star would be constant, then we could have a perfect approximation with no error. But if j star varies a lot, then we could potentially have a very poor approximation with a very high approximation error, which is actually the case in this particular figure.
If you go back to the previous slides, can you explain a little bit further about this footprint set using this graph, like fine grade and so on? What does that mean?
Exactly. So the footprint set is basically the set of states that aggregate to a particular representative state. So the footprint set of X here is just the set of states that we define with the aggregation probabilities to aggregate to X. And in general, you're free to define this however you like. In this case, I've just defined it as sort of a small box with the nearest around that particular representative state in terms of the Euclidean distance, which is one example, but you can define it in different ways as well. So
the gray box would be the footprint set of that X.
Exactly. Are there any questions about this footprint set? Any further questions? Yes.
Oh, if original states to that representative state is always one in the footprint set?
Yes, so for all the states in the footprint set, they're going to have a probability of 1 of aggregating to the representative state of that particular footprint set.
That's for hard aggregation.
Yeah, this is for hard aggregation. So what we're discussing now is hard aggregation. This is a special case, but the whole framework is quite general in that you can design these distributions here, phi, in a very general way. But now we're just focusing on a special case called hard aggregation, where we have this particular constraint that the aggregation probabilities are going to be 0 for all representative states except 1. This is a special case. Okay, and now we'll try to formalize this intuition about the difference between J star and J tilde by introducing a parameter that we call epsilon, which is the maximum variation of J star within one of those footprint sets. So in this particular example, the epsilon value is going to be epsilon 1 here. So we have 3 footprint sets, and in each footprint sets, we have some maximum variation. And then we're going to take the maximum out of all of these 3 footprint sets. And that's going to be this value epsilon. And with this value epsilon, we can now bound the difference between J star and J tilde, which we're going to refer to as the approximation error. And we bound it with the following inequality. Now, this inequality or this bound in general is not going to be tight. So you should not interpret this as a formula for calculating your approximation error, but rather think about it more qualitatively as giving you insight about what factors determine the quality of your approximation. And in this case, the main factor is this value epsilon. So the takeaway is that you want to design your aggregation probabilities, ideally, in such a way that you obtain footprint sets over which J star is relatively constant. And if you manage to do that, you will have a very good approximation with a low approximation error. Yes, please. Alpha is a discount factor. And there's a lot more details about this particular error bound in the course book and exactly how it can be derived, etc. And also more generalization of this particular. So this bound that we present now holds only for the hard aggregation case, but there are extensions and much more available in the course book.
So epsilon here represent the maximum within each footprint set, right? But how, if we like make sure that this is relatively small, how we can make sure that the variation throughout the set is small as well?
Yeah, so this is kind of easier said than done that you try to get this epsilon small. So because, you know, we then generally don't know J star, right? So that's the difficulty. So it's quite hard to design your aggregation beforehand to try to make epsilon small. If you knew J star from the beginning, it would be a lot easier, of course, then you could just fit it. But in general, yeah, it's quite hard to give a general principle for how you're going to design your aggregation probabilities to make epsilon small. It's going to be quite problem specific, but often you have some intuition about your problem and the cost, and you can see what kind of states does the cost vary a lot. And then you probably want to make sure that those are in different footprint sets, because then the cost can vary a lot. And then you try to design your aggregation based on that principle to try to make epsilon small.
So just to do you determine the aggregation probabilities of something that you are defining every given problem?
Yes, so this is up to you as when you apply the aggregation methodology, you're free to design these probabilities. And in general, this is a quite nice thing with the aggregation framework that I'm going to present it here in a very general sense, but when you apply it in practice to a specific problem, there's a lot of opportunities to incorporate domain-specific knowledge, both in how you define the representative states and also in how you define the aggregation probabilities. So there's a lot of opportunity there to incorporate specific optimizations for your particular problem.
So to get your optimal probabilities?
Yeah, a little bit of experimentation is usually good, but sometimes you also have prior knowledge that can be applied directly to design this. Okay, so this is probably the most theoretical slide of the whole lecture, and now we'll move on to an example. But before I do that, just are there any more questions about this error bound here? Good. So before I move on to the example, let me just summarize the, okay, so.
Mentioned about knowledge. So for example, if I have some way to segment my states into similar groups, then that will help to formulate representative states as well.
Exactly. So if you have that kind of knowledge, we saw before an example where we did kind of a uniform discretization. And that can be if you don't have prior knowledge, but if you have prior knowledge, then you can use that to select your representative states. Okay, so before I go to the example, let me just summarize the whole methodology that we covered. It's basically 4 steps. First, you select a subset of your state space to be representative. Then you design aggregation probabilities to relate your representative states to the original states. And that will allow you to formulate an aggregate dynamic programming problem. Then you solve that problem exactly using dynamic programming or reinforcement learning. And that will give you a cost function for the aggregate problem called R star. And then you can use interpolation to obtain a cost function approximation J tilde for the original problem. And we have seen also that in certain cases, you can bound the error between J tilde and J star. And now I will illustrate this whole methodology in applying it to a POMDP. And I also want to make a remark here, and we've asked a question about this earlier, that this framework extends to state spaces that are continuous. And actually in the example now, we're going to apply it to a space that is continuous. So you can do aggregation over continuous spaces as well. And I believe that you covered POMDPs in lecture 4 and also a little bit in previous lecture, but I will just recap it quickly, the problem setup. So the main difference between a POMDP and a regular DP problem is that the state is hidden and not directly observable. And instead you have an observation Z, which is generated with some probability that depends on the state. And given the history of these observations and controls, you can then compute the conditional probability that the current state is I, and that is denoted with B of I. And if you now combine all of these B of I in a vector, then you get what we call the belief state, denoted by B. And this belief is a sufficient statistic for control. So you can define your policy as a function of the belief. And the belief can also be recursively updated with a belief estimator, capital F, which you can think about as basically your system equation in this case, where Z becomes your disturbance term. And this is sometimes called the belief space formulation of POMDP. And this belief vector then resides in some space that we call the belief space, and denoted with capital B. And this is going to be the n-1 dimensional unit simplex. So n here is the number of states of the original problem. So this means, for example, if you have 2 states, it's going to be a unit interval from 0 to 1. If you have 3 states, it's going to be a triangle. If you have 4 states, it's going to be sort of a pyramid, and so forth. And importantly, all of these spaces are continuous, which means that dynamic programming is in general going to be intractable computationally. And therefore, aggregation is a very appealing approach to try to approximate these problems. And that's exactly what we are going to do by simply discretizing the belief space into a finite set of representative beliefs. Now, here's a formula for uniform discretization, but this is not a very important formula to remember at all. You can just note that there is a parameter in the formula called rho, which controls the resolution of the discretization. So it basically controls how many representative beliefs that you will have in your set of representative beliefs. And once we have discretized the belief space in this way and defined a finite set A of representative beliefs, we can then relate those representative beliefs to the original beliefs in the original space by introducing hard aggregation based on the nearest neighbor mapping. So this is a particular instantiation of the aggregation probabilities that we discussed earlier, where we basically partition the belief space into these cells, where each cell contains all of the beliefs that aggregate to the same representative belief. And this is just because they have the same nearest neighbor. And nearest neighbor can be defined in terms of some distance metric in this case. For example, the Euclidean metric. So this is just one particular instantiation of the aggregation probabilities. So are there any questions about this? For illustrative purposes, belief space here is just the two-dimensional simplex. But in general, it can be a much larger space that's not so easy to visualize. But just for illustration, I'm using here a small belief space to show the discretization. And just to remind you, the parameter rho is just controlling the resolution of the discretization. Okay, so we will apply this particular idea of discretizing the belief space to a particular POMDP problem that is called Rocksample. That is a classical benchmark problem in the AI community that has been studied for the last, I think 2 decades actually. And the basic problem is that you have a rover on Mars that is supposed to explore and try to find good rocks. But the challenge is that we don't know beforehand which of the rocks are good. So you need to explore in order to find it. And there are different ways that the rover can explore. It can move around at a certain cost. It can also sample at the current location. So basically dig at the current location and look for rocks. But this can have a very high cost if you don't find a good rock at your current location. If you find a good rock, you actually get a good reward instead. And finally, you can also apply a long-range sensor to check the quality of the rock from a distance. And this is also incurring a cost. And importantly, this sensor is not perfect. So this can give you the wrong answer sometimes. So it's a noisy sensor. And the degree of the noise increases exponentially with the distance to the rock. So the problem is basically that you want to explore, find the good rocks as quickly as possible with as few sensor measurements as you can and with as few samples as you can. That is the best case scenario. And once you have found the good rock, you can also exit the mission by moving to the right side of the map. And then you also get a reward for completing your mission. So are there any questions about this problem? And we will show you some animations shortly. So it's a finite POMDP problem, basically. And in the context of our aggregation methodology, this POMDP has 128 states, which means that our belief space is going to have 127 dimensions. And for our experiments now, we will discretize it with 3 different resolutions. With the first resolution, we only have 128 representative beliefs. So that's basically only the corner points of the simplex, where we only have beliefs where the probability of being a certain state is going to be 1. So it's a very, very coarse discretization. And then we're going to increase it to 8,000 and then to around 350,000. So each of these 3 discretizations will then lead to a different aggregate problem that we're going to solve using exact dynamic programming, value iteration to be precise. And then once you have solved the problem and obtained the cost function approximation J tilde, as we discussed earlier, we're then going to define a policy based on the one-step look ahead in this equation here. And now we're basically going to evaluate this policy and see how good it is. And we are mainly interested in seeing how does the quality of this policy change when we increase the number of representative beliefs? So how important is the number of representative beliefs for the quality of the approximation? And before I play the animation, let me just explain so you can understand it. So these things are rocks, and below each rock, we are going to write the belief, basically the belief that you think that the rock is good. This is going to be initialized as 0.5 for each rock. And then as you apply your sensor and you get more information, this belief will change over time. And the rover is down here, and we can also move around in the map. And to animate the sampling action, I'm going to use just a shovel that's going to be blinking at the location of the rover. So whenever you see this shovel, it basically means that we're doing the control of sampling. And whenever you see this red line, that is going to animate when we do the control of doing a long-range sensor to the particular rock. So you can understand how the dynamics work here. And I'm going to start with the animation where we have a very few number of representative beliefs, only 128. And we're going to see how the policy looks in this case. So quite disappointingly, the policy in this case is very conservative. Since it has such a poor view of the beliefs, it's such a coarse number of beliefs, it basically doesn't even use its sensor or sampling, because it's very hard for it to tell if the rock is going to be good or not. So it just goes directly to the exit area and finishes. So it's not a terrible policy, but it's not a good policy either. Very simple policy. And yeah.
Can you explain what is this episode 1, 2, 3, 4, 5?
Yeah, so basically when I just generated the animation, so I have pre-computed the policy, right? And now I'm just running a bunch of episodes to evaluate how it performs. And these are just you can think about the episode as an evaluation episode. And I'm also calculating the average cost. And you can see here that the average cost, now this is only for 10 episodes, so the sample size is quite small, but it's around minus 9.6. And I think the optimal in this problem is around minus 20 or minus 22.
So how are whether or not a rock is good is decided before?
So yeah, so when the episode is initialized, the quality of the rock is randomized. So you will see when we play the animation here that in some episodes, all of them are good. In some of them, a different subset will be good, and so on. Another thing I forgot to mention is that whenever you sample a rock and it is good, then after you sample it, it will turn bad again. And you will see that later on. So let's now move to a more interesting policy. Hopefully, this is the case when we have around 8,000 representative beliefs, sorry. And now you can see the policy is going to be quite better, but still quite simple. What it does is basically it goes to all of the rocks. And when it is just on top of the rock, it uses the sensor to check the quality. And since you're very close to the rock, the sensor is going to be very accurate. So then you're going to know with belief, it's going to be basically certain if the rock is good or not. And if it's good, then it's going to sample it and collect the good rock. If it's bad, it's just going to skip the rock and then move to the exit area. And you can see that the average cost here is going to be something around like minus 15 or minus 18 compared to minus 9 in the previous policy. So it's significantly better. Okay, then I think we move on to the last policy, which is when we have around 350,000 representative beliefs. And this policy is actually very close to optimal, if not optimal, because this problem is actually so small that you can solve it exactly. And if you compare the policy I obtained here with the exact optimal policy, they are almost the same in terms of cost. So this policy is a little bit more sophisticated in that it uses its long-range sensor sometimes from a distance. And if it figures out that the rock is not good, it will not even bother to move over there. So that's why it's a little bit better than the previous policy. So we also have some experimental results on larger instances of this problem. But before I present that, are there any questions about this animation? Okay, so the basic takeaway is that we see that the performance of the approximation improves with the discretization resolution, which is not so surprising because when we increase the discretization resolution, we also increase the number of representative beliefs. Yeah.
Can the sensor just like detect it from, if it can from distance, can't it just stay there to detect it? What's the requirement of having them move?
Yeah, so first of all, the sensor, if you do it on distance, it's going to be some noise, so it's not guaranteed to be good. And also, to get the reward for a good rock, you have to go there and actually sample it. So you have to move it if you go, otherwise you don't get the reward.
I guess, are you like trading off between like having it to move, because it like move to each rock? They try to like move to each rock, like individually get as close as possible. So like, is there a way to kind of like balance between moving the sensor, or like getting that sensor to the exit point as fast as possible versus like going straight to like each rock and doing like some sort of iterative like pathing sort of kind of scheme?
Yeah, I think there is, I mean, there's definitely some trade-offs here in this POMDP because some count controls are purely for gathering information. So you use some controls like the sensor just to get information so that you later can do another control to get the actual reward. So there is a balance there between how much you explore versus you go and just take the rock you think is best. And yeah, but for this relatively small problem, I think that this policy we saw here is basically optimal. So it's quite simple. Yeah. Yep.
So last animation, are the rocks initialized to bad to begin with?
So the rocks are initialized randomly in the beginning. So some of them will be good and some will be bad. And sometimes all of them are good and sometimes all of them are bad.
It wasn't the sensor detecting from a distance. It was just randomly initialized to good in this case.
Yeah, exactly. And I can see, so you see here, I can show you here. So you will see in the beginning here that it uses the sensor and then the belief of that rock becomes like 0.03 because it uses the sensor from some distance, which means that it's not completely certain that even though it sensed it, whether it's good or not because of the noise. So that incorporates. So again, the takeaway is mainly that when we increase the discretization resolution, we generally get better approximations. And one can also show theoretically that in the limit, as this resolution increases, your approximation will actually converge to the optimal cost function. But there is a fundamental trade-off here because when you increase the resolution, you also increase the number of representative beliefs and therefore the complexity of the aggregate dynamic programming problem. So in this figure here, on the y-axis, you have the number of representative beliefs, and on the x-axis, you have the discretization resolution. And you can see that the number of representative beliefs increase exponentially with this resolution. So in practice, I would say that you typically want to find some kind of sweet spot where you obtain near optimal performance, but still relatively efficiently. And then you typically, there's no benefit of increasing the number of beliefs just for a marginal improvements in performance gain. So this is typically some experimentation you have to do. Yeah. This short, you know, yeah.
In practice, you don't know J-star, so you could say.
Yeah, exactly. You don't, in practice, you don't know. Yeah. Yeah. Exactly. For this particular rock sample, there are benchmarks, so you know roughly, but in practice for other problems, then you don't know. Yeah. But you can then measure and see when it get to some points where you have a very high diminishing returns, where you see that increasing doesn't really improve your performance. That's probably a good indicator that you're quite close to optimal. So we also evaluated aggregation on larger instances of Rocksample. So for example, Rocksample 1010, in that case, we have a 10 by 10 grid and we have 10 different rocks. So it's a much larger problem, more complicated. And we compared it also to most of the state-of-the-art POMDP computational methods in the literature. And details about these methods is out of the scope of this lecture. And you can look it up if you're interested, but I will just categorize them briefly for you. So we have one set of methods that are based on policy-based, so basically approximation in policy space. And these are very popular deep reinforcement learning methods based on policy gradient, for example, PPO and PPG. And then we have one exact dynamic programming method called IP, or incremental pruning, which actually has an optimality guarantee, but it's very inefficient and doesn't scale, as we will see in the example. And then we have a bunch of methods based on heuristic search. And these are basically derivations of Monte Carlo tree search that you saw in the previous lecture. And then you have a couple of methods that are so-called point-based, which has some similarity with aggregation, but is still quite different because they use a different dynamic programming operator than we use in aggregation. In aggregation, we use the classical Bellman operator, whereas in point-based, they use a slightly different one based on so-called alpha vectors. And you can look it up if you are curious about this. And here are the experimental results. So the first number in each cell indicates the cost, and the second number indicates the compute time in minutes. And aggregation is the first row. So the main first thing to note here is that many of these methods does not scale. So when I write NA, it means that I could not obtain a result in 24 hours of computation because they simply did not produce anything. So you see that many classical methods like incremental pruning, point-based value iteration, this SARSOP method, they do not scale. As soon as you get to a problem of a certain size, you cannot use these methods anymore. In contrast, if you look at aggregation, it scales very nicely. So you can always adjust the computational complexity by tuning your aggregation. And therefore, you can apply it to quite large problems quite easily. In terms of performance, we see that aggregation is not the best on all the problems, but it's always near optimal. So it's a very reliable method. And for example, if you compare it to policy-based methods like PPO or PPG, it is significantly better for this case. So I think the takeaway, another nice property of aggregation compared to the other methods is that aggregation, as we saw, has certain theoretical performance guarantees, whereas many of these methods are mainly based on heuristics and lack such guarantees. So I would say that the main takeaway is that aggregation is a very scalable method that can give you very near optimal performance in practice. And it also has this nice benefit of theoretical guarantees in certain cases. So before we go to the break, are there any questions about these results? So I basically run it until the method converges, or when it doesn't converge, I just put some arbitrary limit. Like for example, PPO, I just put the limit to 1,000 minutes. But if the method converges, then I denote the number of minutes it took to converge. Yeah, the implementations of aggregation is my own. All the other methods are based on, this is a standard benchmark problem. So they are publicly available implementations of these. Most of them are written in Julia, and you can run them, and they are very efficient implementations. So I'm using those implementations for the comparison. Yes.
So looking at this chart, last method, POMC, POW, seems to be performing consistently better than aggregation. So two questions I have. First is why, or is it correct to say that aggregation is a better method to use comparatively? Second question is for that last method, irrespective of the number of belief states, is it just consistently computing and solving the problem in approximately 1.6 minutes?
So, okay, so first of all, I think POMDP, so we want to minimize cost, right? So aggregation actually has a lower cost compared to this one in most cases, in actually every case. So that's one case. The other thing is that, yeah, I forgot to mention this. So some of these methods are actually online methods. They are Monte Carlo tree search methods. And then it's a little bit difficult to compare in terms of computational time because they do much more work per control step, whereas we do all of the work offline. And what I did here is that I were given all the online method 1 second per time step for the control. And then I think then we basically got to 1.6 minutes if we combine all the time steps. And I think the reason I chose that was because this is how most of them are using in other benchmark problems that they use that much time. But yeah, this is a little bit awkward that all the costs are negative, but that is because this problem is usually defined in terms of reward. So that's why I interpret it in terms of cost for the purpose of this lecture, but that's why all the costs are negative. Okay, so then we take a 15-minute break, and after the break, we will cover a more general aggregation framework and also a cybersecurity case study. Okay, let's start. So in the second half of the lecture, we will cover general aggregation. So it's basically an extension to aggregation with representative states. And then we will do a quite detailed case study of using aggregation in the context of network security. So starting with the general aggregation methodology. And the main difference here is that now we are not going to associate each aggregate state with a single original state. So we're not going to assume that the aggregate state belongs to the original state space, but rather we're going to associate each aggregate state with a subset IX. So each aggregate state is associated with a subset IX. And this is more general and quite useful in practice because sometimes you want to have this association between the aggregate state and more than one state of the original space. And now just to make sure that you are alert after the break, I have a question for you. And that is, why is aggregation with representative states a special case of general aggregation?
The aggregate state may not be in the original state space. So if it's, the original state space is, for example, discrete and the point of view between some of the states, then it's not necessarily going to be a part of the original state space.
No, so for the representative state, it will always be part of it. So that's not the case. There's another reason. So the clue here is that we associate each aggregate state with a subset, but we don't say anything about the size of this subset. So what happens when this subset is just one element? Yeah, so when the IX is just a singleton, just one element, then it's effectively equivalent to an aggregation with representative states. So aggregation with representative states is indeed a special case of the general framework. Apart from that, the rest of the framework follows along in a very much similar manner. So we're going to associate each aggregate state with an aggregation probability distribution denoted by phi. That tells us the probability to go from each original state to each of the aggregate states. And the main difference now is that since each aggregate state is associated with more than one state of the original space, we're also going to need disaggregation probability distributions so that we can transition. Yes?
What's the difference between general aggregation and the hard aggregation?
So hard aggregation is a condition for the aggregation probabilities. And you can define hard aggregation also in this case. But aggregation, general aggregation framework is different from the aggregation with representative states in how we associate the aggregate states with the original states. But then how you define the aggregation probabilities, this is still a very flexible parameter in both cases that you can define with hard or soft aggregation.
Here we still have these joint subsets and the probability sums to one, same as in the hard aggregation. So it seems to me that the condition is the same.
Okay, so let me think. Yeah, so it's a little bit different in this case that, yeah, you're right that all of the states that are in the subset I of X, in their aggregation probability, they should aggregate directly to the particular aggregate states. That is right, yes. So that is indeed similar to hard aggregation in the case of representative states, the condition. Any other question about this?
I just want to make a clarification that you give a all set of IX, and all of them combined together is not necessarily cover the entire state space. So for example, if you have A, have only 2 aggregate states, and you would have I1 and I2, and I1 and I2 are disjoint, but their union is not necessarily cover the entire state space. So whereas in hard aggregation, you will have the footprint set of S1, S2 cover the entire state space. So that's a difference.
Thank you. So then the difference is that we now have the disaggregation probabilities to be able to transition from an aggregate state to a particular original state. Since we now have this association with a whole set of states, we have this mechanism with disaggregation probabilities to single out a particular original state for the transition. And that transition dynamics is then defined with the disaggregation probabilities down here, which we denote with dxi. And with this, equipped with these disaggregation probabilities, we then obtain the following dynamical system, very similar to before. The main difference now is this vertical arrow going up from the aggregate state to an original state. So we essentially have 3 types of transitions. We can transition from an aggregate state up to an original state using the disaggregation probability. We can go across using the dynamics of the original problem, and we can go down again from an original state to an aggregate state using the aggregation probabilities. And this dynamical system then, just like before, will allow you to formulate an aggregate dynamic programming problem that you can solve. So in that way, much of the previous framework carries over. But the main question here when you use general aggregation is, how do we select those aggregate states? And there are different ways that you can do this, but one of the most principled ways and common ways in practice is so-called feature-based aggregation, where you associate or have a feature mapping that associates each original state with a set of features that describe the states in some way, properties of the state. And these features are often comparable. So then we can use those features to form the aggregate states by simply grouping together states that have similar features. And how you obtain the features in the first place, this can often be like a property of the problem to begin with, that you have features. In other cases, it can be that you have domain knowledge that allow you to construct the features yourself. And in a third case, you may actually automate this process and learn the features from data using deep learning. And there's a lot of information in the course book in how you can do this. So basically, you take your state space, you map that to a smaller feature space, and then you can aggregate states based on the features. So are there any questions about this particular idea of feature-based aggregation? Because we will see several examples shortly in how we can apply this in the context of cybersecurity. Okay, so that concludes like a brief coverage of general aggregation, and there's more details about it in the course book. But now we will shift gears a bit and see how we can apply general aggregation in the context of cybersecurity. So to warm you up a little bit, this is a security operations center where human operators sit around the clock and they analyze monitoring data and try to figure out how to respond to different incidents and potential attacks. And in fact, during my bachelor studies, I used to work night shift in one of those. And right now, globally, we have a global shortage of around 4.8 million of these operators. So that really motivates the question, whether we could automate some of those operations. And the answer to that question, in my view, is a definite yes. And we have developed an adaptive control methodology for this purpose, which builds on many of the concepts from this course and which can be understood on a high level through this picture here. So the starting point is that we have what we call a target system. And this simply corresponds to the system where we want our security policies to be operational in the end. So this is where we want to run them in the end. But for safety reasons, we cannot really do experiments directly on the target system. So what we do instead is that we first take the configuration of the target system, and then we emulate it to create a virtual replica that runs the same software exactly, but on virtualized hardware. And that replica then provides us with a safe environment where we can run emulated attacks, we can run controls, we can investigate and see what kind of security policies are more effective against different types of attacks. And such investigations then generate a lot of measurement data, which we then use to identify a mathematical model of the system. For example, a POMDP model. And given that model, we can then apply dynamic programming techniques to approximate a near optimal security policy for the problem. And then we take that policy and we experimentally validate it on this emulation system to basically make sure that it satisfies safety properties and is that we trust it for operational deployment. And if that validation is deemed successful, we can also implement it on the target system. So this is a very general methodology that can be instantiated in a broad variety of ways. And I will just focus now on a particular instantiation related to aggregation. But before that, are there any questions about this method? Good. So we will focus on a particular target system that consists of a set of interconnected components that jointly provide a set of network services to clients, for example, web services. And some components may be compromised by an attacker. And the problem is to find a security policy that uses measurement data from the system to prescribe effective security controls. And I will shortly explain more details what kind of controls we consider. But in general, it can be anything that you can do to reconfigure the system to prevent or mitigate an attack.
So the one highlighted in red, what does that mean?
So in this case, I just use red to highlight that this component is compromised by the attacker, basically accessible to the attacker. And in general, I will use red to denote when a component has been compromised. That's a good remark. And mathematically, we can think about this problem as a form of a POMDP, where the hidden state represents the security statuses of the different components, which generally we cannot measure directly. So typically, we always have this uncertainty that we cannot directly detect a potential attack. There's always a delay in detection. So therefore, the state is hidden. And you can consider an example, for example, if you have m components, then this could be a vector where each element in this vector is a binary variable that is 1 if it is compromised and 0 otherwise. So that's the state of the POMDP. Then for the observations, then it's much more diverse. Observations can be almost any measurements that you can collect from the system. This could be log files, performance metrics, or kind of security alerts. So often these kind of systems run a lot of anomaly detectors that generate alerts in real time. And those alerts are a very typical observation in this case. So in the figures here, we have two empirical distributions of security alerts on our testbed for two different types of attacks. And the attacks are identified by these standard identifiers. And if you're curious, you can Google them and you can find out what kind of attacks we're talking about. And the blue, so basically on the x-axis, you have the number of security alerts. On the y-axis, you have probability. And the blue histograms show the distributions during normal operation, and the red one show the distributions during an attack. And what we can note from these distributions are that there's quite a lot of false alarms. That's why the distributions overlap over here. But there is also a pretty clear statistical significance difference between these two distributions. And that could then potentially be used to detect the attack or to refine the belief later on. So this would then be your observation distribution in the POMDP. And regarding the controls, this can be almost anything to reconfigure the network, but here's just 3 examples. So one control will be flow control, where you dynamically reprogram your network topology to redirect network flows and try to isolate potential suspicious network traffic. Another control is access control that you can use to constrain the movement of a potential attacker to not allow it to access certain parts of the system. And another example would be replication control, where you can ensure that critical services have multiple replicas and can continue to maintain service even when some replicas may be compromised. And when we choose between these controls, the primary objective is to minimize the impact of a potential attack. But at the same time, we also would like to maintain services to our clients. So it's kind of a bi-objective, and it can be understood on a high level through the following graph, where on the x-axis you have time, and on the y-axis you have system performance and security. And at some unknown point in time, indicated by the left dotted line, an attack event may occur. And when that happens, we would like that the system maintains some acceptable level of performance and as quickly as possible recovers to normal performance again. And this can then be encoded in a cost function that we would like to minimize. So that is our cost function in the POMDP. And just to give you an example of how we can instantiate a POMDP in this context, we can say that we have M system components. Each component has a state variable that can be either 1 or 0, where 1 means compromised. Each component also has an observation variable that can take values from some larger set that indicates security alerts. And for each component, you also have 2 different controls. You can either wait and do nothing, or you can do recovery at a certain cost, where recovery will always turn the component from state 1 to state 0 if the component has been compromised. And the objective here is that you want to minimize the number of compromised components at all times, but at the same time, you do not want to do excess recovery. So you don't want to do recovery unless it's really needed. But of course, the challenge here is that you never know exactly if the component is compromised or not. So there's always some uncertainty that you express with your belief. And based on that belief, you decide if you're going to do recovery or not. Yeah.
So can you, at each stage, you do recovery for one server or multiple servers simultaneously, or?
In this particular problem, you can do it for multiple simultaneously. So you have quite a big control space as well, since you can choose a control for all the components simultaneously. So you have a multi-dimensional control space. And even for this very simple problem, I mean, this is really a toy problem. We run into this fundamental challenge that is very typical in this domain. And that is the well-known curse of dimensionality, where the complexity of the problem grows exponentially with the number of system components. So this is because we have typically at least one state variable per component and at least one observation variable. And then when you increase the number of components, you get this combinatorial explosion of all the possible combinations that makes the size of the state space and the observation space simply take off. And this is really problematic because this means that these kind of problems you cannot solve them for any non-trivial system because you're going to have much more than 14 components. And that's why aggregation is a very appealing approach to try to approximate these kind of problems. And that's exactly what we are going to do next. Yes, please.
One system depends on control of other systems. For example, you choose the control of one system, does that affect the control of the other system?
So I didn't define the dynamics here, but potentially it could in some cases. For example, say that the control, if you go, yeah, say that the control is that you say change the topology in the network here. Then this will also affect the other servers or the other components because now the attacker cannot reach on the same path to that one. So in some cases it can affect, but it depends on the problem. It depends on your dynamics.
This be a case solved using multi-agent
rollout. Yeah, multi-agent rollout is a very good option in this case, since we have a high-dimensional control space here. So this is like a perfect case for multi-agent rollout, although this is not the focus of my lecture today, but this is definitely a good use case. So to tackle this high computational complexity, we use a version of the general aggregation that we discussed earlier. And in particular, we use a form of feature-based aggregation. So the main issue we have is that since the state space is so large, it could be 10 to the power of 50, for example, the belief space has such a high dimension that it's really impractical to work with, and it's impractical to even discretize it. So therefore, we use features where we first map our state space into a smaller feature space, and then we construct beliefs over those features, and then we aggregate them into representative beliefs. Very similar to that what we did for the Rocksample problem. So the only difference now we had this extra step with features to simplify the problem and reduce the dimension. And I will show you some examples of how we can define features before we show some results. So here's an example infrastructure with 64 components. And let's continue with our example where each component only has a binary state. It can be compromised or it can be safe. And in that case, we would then have 2 to the power of 64 states in this particular example. And as a result, the belief space will have dimensions in the same order. So to tackle this, we then introduce the features to simplify the problem. And let's look at the simplest possible feature for the problem. And that could be that we just introduce one feature that says, is the whole infrastructure compromised or not? So we basically treat the infrastructure just as a black box. Is it compromised or is it not? And we don't really pay attention to which components are compromised. So that would be a very coarse-grained feature aggregation. And then your belief space will be very, very simple, just one-dimensional. And then, of course, you can make this more fine-grained by introducing more features. So we can, for example, segment the network into different zones. And this is, by the way, how networks are operating in practice. So, for example, the university network here probably is segmented into different zones depending on the departments and so on. So then we could have one feature for each zone that tells you if the zone is compromised or not. And you can then continue this, breaking down the problem even further into 4 zones or even more zones. And depending on how many features you have and their possible values, your number of feature combinations will increase, which will make the aggregate problem more complicated. But for our particular animation now, we will look at this particular case where we only have 4 features and therefore 16 possible feature combinations. And we will then construct beliefs over the values of those features and then discretize the belief space, just like we did for Rocksample, into representative beliefs. And we will use around 200,000 representative beliefs. That then defines our aggregate dynamic programming problem. We solve it using value iteration. And then we use the resulting cost function approximation J tilde to obtain our policy mu, which we are now going to evaluate. Yes? Yeah, uniformly in this case as well. Yeah. But this could be done more Specifically, if you have some intuition about some zone being more important than the other, maybe you want to have more beliefs in that area, for example. So just to teach you about the animation before I run it, it's going to look something like this, where we have, for each zone, there's going to be a belief that is dynamically changing. So this is the belief of compromised. 1 means compromised. And you're going to see how they change over time. And in the bottom, you're going to be able to follow the time step, the cost, the control, and the average cost per time step as it accumulates over time. And to animate the controls and the attacks, I will use this symbol here to indicate an attack. And I will use this cross here, the aid cross, to indicate a recovery of a server. So whenever you see this blinking crosses, it means that we're doing recovery. But you will also be able to read it in the bottom. Yeah, the cost is basically like this. So I didn't give the formula here, but it's basically a sum formula where you want to minimize the number of compromised components. So basically the sum of all the states, because the state is going to be 1 if it's compromised. You want to minimize that sum. And you also want to minimize the sum over the controls, because the controls is going to be 1 if you do recovery. And each recovery incurs a cost. So you only want to do recovery if you're certain that there is, or quite certain that there is an ongoing attack. And then you can have some weighting factor to say how important it is to prevent attacks versus how costly the recovery is.
So for any compromised zone, we have cost of 1 for recovery.
So the cost of 1, yeah, if you do recovery for all the nodes in a zone, then the cost will be proportional to the number of components in the zone. That's the cost. And similarly for the compromise cost, but you can have, like I said, weighting factor there. Typically you weigh the cost of an attack more than the cost of doing recovery. But this is really depending on something you can tune. Okay, so then I will play the animation. Now you can see that there's already some attacks in the system. And you can see how the beliefs are evolving over time based on the observations that we collect. So the security alerts in this case. And it's a little bit hard. This animation is not the cleanest, but basically I can explain the policy. If you study this animation for some time, you can see that the policy is basically that when the belief of compromise in a given zone reaches around 0.15, then the control policy does recovery of all the components in the zone. That's the basic policy that it has learned. And I think it's quite clear that if you would have more features, so more fine-grained beliefs over the nodes in each zone, then probably the control policy will be very different, where it will recover only specific components instead of the entire zone, for example. And also this threshold in how far the belief has to go before you do recovery also will depend on how good your sensors are of the attack. So if you have very good sensors, then maybe you can wait until you're more certain and so forth. So are there any questions about this before we go into the final part of the lecture? In this case, yes, it's just the understanding of the problem. But in more generally, you could try to learn the features from data. But in this case, it's based on domain knowledge, essentially. So in the final part of the lecture, we will look into the fact that aggregation is an offline methodology, which means that you can combine it with online play very nicely. They fit together very nicely in the more general approximation in value space framework. So here's a schematic of how it could look like in the context of cybersecurity, where in the bottom, you have the offline part, where you use aggregation to optimize a cost function approximation and a base policy based on the aggregation of the belief space. And then you can utilize that during your online control cycle that you see in the top part, where at each control cycle, you would use measurements from the system, for example, security alerts, to estimate a belief. This could, for example, be done with a particle filter, which would be used in our experiments. And using that belief together with your base policy and the cost approximation, you can then refine the policy using rollout and look ahead optimization to obtain an improved rollout policy. And then you use that policy to select your next control. And another very powerful feature of this framework is that it can be adaptive, because often these network systems are very much dynamic and non-stationary. They change very frequently. And then you can utilize rollout to adapt the policy computed offline to changes in the system. So that's another very nice side effect of this, apart from just improving the policy. And we applied this framework to a standard benchmark problem in the security literature. And right now, all of the state-of-the-art methods evaluated on this benchmark are based on deep reinforcement learning. So PPO, PPG, DQN, and so forth, as well as some methods based on Monte Carlo tree search, so POMDP. And we evaluated aggregation on this benchmark, both plain aggregation and aggregation with rollout. So the first column indicates the method. The second column indicates the compute time, both offline and online compute. And pay attention to the unit, which is minute for the offline computation and seconds for the online computation. Then the third column indicates what is used for state estimation. So all of the deep reinforcement learning method that are state-of-the-art on this benchmark, they don't even do any state estimation. They just feed in the latest observation in the neural network to select the control. But to enable a fair comparison, I also evaluated them with the particle filter for state estimation. And the fourth column is the cost that we want to minimize. The first thing that we can note, I should also say that the blue line here is the previous state of the art. And this is PPO, which you are familiar with, plus some heuristics for doing action pruning. So this is actually not a very general method. It's very specific to this benchmark where they have fine-tuned the action space based on the problem. And that was the previous state of the art. Now, if you look at the performance of plain aggregation with no rollout, is actually within statistical significance. There's no statistical significant difference between aggregation and the previous state of the art. They are actually in the same range, almost at least. And then if you combine aggregation with rollout, we can see a very clear performance improvement where we vastly improve the state of the art actually on this particular benchmark. Now, we have a lot of details about these experiments in our paper that we will release soon with many different configurations of rollout. But for this particular best result, we used a look-ahead horizon of 2. I've used truncated rollout with horizon, so rollout horizon 20 time steps. And then we used truncation with the cost approximation obtained from the offline aggregation. That was what gave us the best result. And you can see also in terms of compute time that our method is actually much more efficient than the previous method. It only requires around 8.5 minutes of offline training to solve the aggregate problem. And then it requires around 15 seconds of online search or online rollout simulation to improve the policy. Yeah, the reason why they take a long time is just, I mean, I run them and I see how they converge. And I basically, if they don't converge, I just continue running them until 1,000 minutes. And if they haven't received any good result, I just stopped it. But that's basically the nature of them, that they take a long time to converge usually. They need to do a lot of trial and error to learn usually. And actually, this one for the heuristic method, now I've managed to optimize it down to 300 minutes. But the first time, like the original reported results for this method required around 48 hours of training. But now it's been optimized quite a lot. So they are significantly slower in this case.
Explain a little bit further the aggregation method, like aggregation solve a lower dimension problem, and how does that? Do you use one step ahead for that, or how do you get? So what exactly the method aggregation mean here?
Yeah, so in this case, I haven't gone in all the details here, but we have used hard aggregation for solving the aggregate problem. And then we have defined the base policy by simply taking the policy for the aggregate problem, the greedy policy, and then mapping that to the corresponding belief in the original problem using the nearest neighbor mapping. And I should also mention here that since the belief space in this problem has a dimension of around 10 to the power of 40, we have used a smaller dimensional belief space based on features. So again, we use the feature approach because you simply cannot discretize the original space. It's so high dimension. So we have used features in this case as well. And the resulting problem has around 427,000 representative beliefs that we solve with value iteration. Yeah.
So what would you attribute the standard deviation and like the deep reinforcement learning algorithms to?
Yeah, I would attribute this, or actually I'm quite certain about this because I ran them with many random seeds. And what happens is that they sometimes get stuck in a local optima on a very, very bad policy, and they cannot really recover. And they can get a very high cost for a certain random seed. And then you run it with a different random seed, and then it can converge to a much better policy. So it's a very high variation of these methods. And you typically need to try many random seeds before you get a very good result. And the main reason is that when you run them, when they converge to a policy that is quite bad, then they will start collecting data with the bad policy, and they cannot really recover from that and get stuck in a local optima in many cases. Any other question?
These are the first order methods.
First order methods?
Like first order optimization.
Yeah, the first order, they're based on policy gradient, but they actually use they estimate the policy gradient based on data. So it's not the true policy gradient. And they also typically they use a discount factor inside it. So it's not really the policy gradient, but it's a variant of it that they use that works well on some problems. And if you do action pruning, then it works quite well on this problem as well. But if you don't do action pruning, you get very bad results. So if you just take it off the shelf and run it on this problem, it doesn't work very well. Yes?
Is it possible for you to increment the online compute with the other methods so that we can have better performance?
Yeah, that's something could be explored, like combining PPO with rollout, for example, to the online. That's something I haven't explored, but that's definitely something that could be done. And I believe that in, for example, AlphaZero and so on, they use PPO offline and then combine it with Monte Carlo tree search online. So there is a possibility of doing that, but I have not explored it. So this compute time here is just the time it takes for the neural network that is trained offline to predict the next control. So I have not done rollout. Okay, if there's no other questions, then I will conclude this lecture by saying that aggregation is a general offline methodology for approximating dynamic programming problems. And it basically consists of 4 main steps. First, you aggregate your original states. You group your states into a smaller set of aggregate states. Those aggregate states then form a new dynamic programming problem that you can solve exactly. And then you use the solution to that problem to form a cost function approximation to your original problem using interpolation. And that cost function approximation can then be combined with online play and so forth to obtain very strong policies for the original problem. And thank you very much for your attention. And now I will hand over to Yushao to say a few words about the next lecture.
Yeah, for the next lecture, we're going to talk about dynamic programming for minimax problem. And then we're going to talk about rollout and approximation in value space for minimax problems as well. And as a case study, we're going to demonstrate a meta algorithm for computer chess based on reinforcement learning, whereby we try to approximate the maximizer in the minimax problem using a given chess engine and demonstrate how a two-player game or two-player problem can be transformed as one-player problem. And for this part, you can look at the section 2.12 of the course book. You are also recommended to look at the video lecture given by Professor Brasikas on computer chess with model predict control and reinforcement learning at this link. And I would also like to just comment briefly about the final lecture after this lecture, which will be on the policy optimization. And for the question one of you mentioned earlier about the high variation about policy optimization method. And in fact, in the course book, we have exercises demonstrate a very simple case with two-state problem, whereby starting from some initial conditions, basically you flip a coin and one side is heaven and one side is hell. It's like one side is local minima and you get stuck there and never get out. And the other side is global optima and in a wide range of initial condition, it's basically pure luck. You flip to one side or the other side and it's complete luck. And by looking at that example, probably you will have better understanding about why in this case study King discussed there could be a high variance of the result provided by policy optimization methods. Okay, thank you for your time.